Meanwhile, under the same rigid secrecy, the Bell Aircraft Corporation had been designing, laying out and building the Air Comet to be powered by the new engine. They too had performed miracles of production in a startling new field.
I can't get used to working on a plane without a propeller.
Neither can I. I hope it flies.
There were a lot of other people who hoped it would fly too, from top brass to Joe Average Man walking along Main Street, USA. Of course, he wouldn't hear about this particular plane for 2 or 3 years, maybe never. But he's a guy who carries deep within him a hope and conviction that any plane America builds will fly. These are the original films of the first jet plane ever to fly in America. That first flight on October 1st, 1942, less than a year from the start of the project, jet-propelled flight in America became a reality. They had gotten off to a flying start, but in a race, it's the stamina that counts. So everybody kept right on working. The original engine, the IA, delivered 1,400 pounds of thrust. It was soon followed by another engine with more power, the I-16 with 1,600 pounds of thrust. Then came the J-33 with 4,000 pounds of thrust, and the jet engine really came into its own. The first flight of the J-33 was in June of 1944 in a Lockheed F-80 shooting star, again less than a year from the start of the project. This outstanding plane set many records, such as coast to coast in 4.5 hours, and became our first operational jet fighter. In order to get the jet industry moving and in the interest of national defense, GE passed along its plans to other manufacturers. Allison Division of General Motors soon began mass production of the J-33 engine to help meet production requirements of the F-80 shooting star. The British Whittle engine and the first engines designed by GE used compressors of the centrifugal type. In these, air enters the hub and is hurled radially outward. However, even prior to seeing the British engine, work on an axial compressor had been started with the National Advisory Committee for Aeronautics. In this compressor, air flows in a straight line to the rear. The axial compressor increases the engine's efficiency and handles a greater volume of air without increasing the engine's diameter. Long-range research led to an axial flow J-35, which powered the Republic Thunderbolt, and the Douglas Skystreak, holder at that time of the world's official speed record of 640 miles per hour. 8 of these powerful new jet engines were also used in Northrop's 100-ton Flying Wing and many other planes in the rapidly developing jet field. During these years of progress with land-based aircraft, the Navy had worked with the McDonnell Aircraft Corporation and Westinghouse to develop the Phantom. Proof that problems associated with carrier-based aircraft were not beyond solution came with the Phantom's first takeoff and landing from an aircraft carrier. Meanwhile, a school was established at General Electric to train the people who would install, operate, and service their new GE jet engines. One of the courses given is simply a general familiarization with the principles of jet propulsion and the jet engine.
Ever since man undertook the conquest of the air, he has had 2 primary considerations. First, the aircraft itself, and second, its method of propulsion. Needless to say, he has not always been successful. Sometimes the airframe itself has been unsatisfactory. At other times, the method of propulsion has lacked the necessary power. In this case, for example, it's extremely simple. While in this, it's so complex that it borders on confusion. Actually, the early attempts at propulsion by reaction were not associated with aircraft. And, as in the case of most of man's early endeavors, they led to some rather startling results. The principle itself is very simple. Newton's third law of motion states that for every action, there is an equal and opposite reaction. For example, an ordinary rotary lawn sprinkler turns because of the reaction of the arm to the action of the jet of water. It does not turn because the water squirted out pushes against the air. It would spin just as well in a vacuum. Similarly, the jet plane flies because of the reaction to the jet. It does not fly because the jet pushes against the air behind it. The engine itself consists of two main rotating elements, the compressor and the turbine, which are both mounted on a single rotating shaft. Air is drawn in, compressed, and packed into the firing chambers where fuel is injected. The constantly burning fuel tremendously increases the energy of the enclosed gases, which rush through the turbine and out of the tail cone. The turbine, operating like a windmill, supplies the power to spin the compressor. The expanding gases pushing their way out of the rear at about 1,200 miles per hour give the plane its forward thrust.
This, then, is the simple principle of propulsion which changed the whole outlook of the aviation industry. By 1951, GE's production models were delivering more than 5,800 pounds of thrust, a five-fold increase in 10 years. These engines are being mass-produced at both Lynn, Massachusetts and the great new Lockland, Ohio plant, the jet center of the world. Lockland represents more than huge production facilities. It represents a new production plan. Thousands of suppliers and subcontractors contribute to the manufacture of the jet engines, which are assembled at Lockland. Thus, all sources of supply, down to the smallest individually owned machine shops, are benefited by the program and kept mobilized for production. The Lockland plan is truly another milestone. Just as the engines which roll from its production lines are the end product of many milestones, the result of almost 50 years of the best thought and effort of executives, engineers, scientists, and skilled craftsmen doing the work they are best fitted for in their own way. This freedom of effort is, after all, the real heritage of all Americans, and the engines are living up to that heritage. Today, General Electric turbojets are doing their job powering the great new planes they were designed for. Such planes as the Republic XF-91, high-speed, high-altitude interceptor. The North American F-86D. The Martin XP-51 superfast tactical bomber. The North American Sabre, holder of the world's official speed record of 671 miles per hour and the 100-kilometer closed course of 635 miles per hour. The North American B-45 Tornado, the first operational jet bomber. The Boeing B-47 Stratojet bomber, which in 1949 flew non-stop coast-to-coast in 3 hours and 46 minutes. And the mighty Convair B-36, the intercontinental bomber, which is powered by 6 turbo-supercharged piston engines and 4 jets. These and others are the planes which must maintain the common security of the free peoples of the world and thereby ensure peace. And maintain that security we will. In one 6-month period, 3 new GE engine designs were okayed for production, each more powerful than the preceding one. The last of these is no larger than the model then in mass production, yet it delivers so much more thrust that it is not even in the same class. Even so, by the time any new engine is in mass production, still newer and better engines are on the way. Engines that will be a tribute to the life work of Dr. Moss, who died in 1946, 1 year after being awarded the Collier Trophy, aviation's highest award. Moss's work is finished, but there will always be others to carry on with new ideas. Perhaps we will travel from coast to coast in 3 or 4 hours of quiet, vibrationless comfort. Certainly our energetic and progressive aircraft industry will give us commercial jetliners as soon as the time is right. Even the atom may release its giant strength for aircraft. The Atomic Energy Commission, the Air Force, and General Electric are already cooperating on an atomic power plant for an aircraft to be built by Convair. NACA, the U.S. Navy's Bureau of Aeronautics, and a number of private corporations are also making real contributions to this program. Developmental engineering moves forward with great new facilities such as GE's Aircraft Gas Turbine Laboratory. Here engineers can simulate conditions for tomorrow's aircraft. Here, men look ahead at the requirements of the planes of the future, requirements established by the product planners of the engine builders, of the airframe builders, and of the aircraft users. These are the molders of aviation progress. As long as imagination, research, design, test, and mass production continue year after year in a never-ending, constantly improving chain, there is no limit to the future of the aircraft engine. And so the jet story grows. In 10 years, we have come from this to this. No one can foretell the tremendous strides the aircraft industry will make in the next 10 years. Yet we can be sure that the engines will keep pace. The engines that are keeping and will always keep America strong.